Just a note about how the slides are structured. So basically, there's more slides here about point-to-point communications, talking about send, receive, etc. So this we will go to after looking at the exercises for the collective operations that we looked at in the past hour. So I would like you now to jump, basically, if you're following along with your slides, jump to slide right. So this is slide in the bottom right, it says 28 out of 57. And so we will begin these exercises. First, you rightly pointed out that I haven't opened up the permissions yet for this. That was intentional because there were some last minute tweaks. I will do that now. Oops, G pass read execute. I think that should, sorry, mod. So now, oh, I don't know why that's not. Well, yeah, so you guys now should all be able, well, so let's see. Yeah, so those are the solutions. Those remain read-only to me by now, for now. And then the exercises are under this EX folder. So if you are in your home directory, please copy paste this command, copy minus recursive, and there you should see the EX folder, it's exercises. And let me say a few things about the exercises, so please pay a bit of attention to the slides for this next couple of minutes. So they follow a common structure. I assume that the previous training event, you know how to log into Cyclone, navigate the file system, modify files. You know what the Slurm script, Slurm scheduler is, even though I've prepared scripts for you. So even if you don't remember too well what this does, you should be okay. And you're familiar with the module system, but again, this has all been prepared for you. Each folder under EX, so if I list the contents of this EX, you see 10 exercises, okay? EX from 0, 1 to 10. Then you will find, in each one of these, you will find a make file, you will find a C source code file, and you will find a submit script. So these are always contained in the in each one of these exercises folders. Some of them have additional files. Okay. Right. So the workflow will typically be modify the C file as instructed for each exercise, compile it using make, submit the job scripts using sbatch sub and the number of the exercise.sh, and then we look at the output, which will be always named like this. Okay. If you do your modifications correctly, but none of these jobs should take more than a minute to run. So these are very short exercises. And anyway, the job script has a cutoff at 1 minute. Okay. Okay, so the exercise is mostly complete, but they require some very minor modifications by you. And this is mostly to encourage you to read and understand the code in order to make these modifications. So here is the list of the first 8 exercises and what they cover. So these 2 we will do after also reviewing the slides on point-to-point communications. So we will basically look at exercises 1 to 6 at this point within the next this might require more than an hour. So we'll see how we go and what the pace is, and see where we get to. So all exercises I have tested with the OpenMP implementation, which is installed on the cluster, and the GNU compiler. So this combination you can load by using module load compy. So that's GNU compiler and OpenMPI is a shorthand for that combination. So please all do that now before we start. Module load GOMPI. Okay. So that means that now the default compiler, when I say MPI-IC, will be GNU. It's calling the GNU compiler, and if I actually see where this is installed, in case you're interested, this is what it aliases to. Okay, exercise 1. So this is exercise 1. Please all change folder into x/x01. Oops, 01. Okay, so this one is pretty simple, but let's since it's the first one, maybe we should take it a bit step by step. So there's 3 files in here. So if you don't know what a makefile is, don't worry. It's just a file with instructions on how to compile a program. You don't need to know what's going on here, other than the fact that this actually it's a tool, so that you don't need to type MPI-IC blah 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 all the time in the command line. Okay, so that's one of the 3 files, the make file. The next file is the submit script. We'll look at that later. And exercise 01.c is the C file that we want to modify. I've opened it up here in another window on Emacs. Hopefully you know how to do it from your end. So this is what this C file looks like. So I'm doing something a bit more than just initializing. I'm also getting the host name of the node that this MPI program will run on. So what we have here is MPI comp size and MPI comp rank, these 2 functions, the first functions that we learned about. And I have to do here for you to fill in the missing arguments. Okay, I've already declared the variables you need to use. Please go back in the slides and see how to fill this in. And then when you do that and you feel confident that you're done, then you can type make, and this will compile the file. If I do it now, it will give me an error because I don't have any arguments here, but I'll show you. So you'll try to compile and it'll spit out all these errors. When you do it, it should be without errors, and then you will have the X01 executable compiled, and that means that you can submit the job scripts. So let's look at the job scripts. Okay, so this is the job script. These SBatch commands should look familiar to you because you probably covered them in the last time, but just to talk about this specific case, we want to use 2 nodes and 8 tasks in total. So when I do this MPI run, or when the script runs its MPI run, then it should run on 2 nodes and 4 MPI processes per node, so 8 MPI processes in total. Okay, and then you will see the output in x01.output, and the output should be, going back to the C program, should be this is rank 0 of nproc 8 on node, and it'll say what node it is. Then it should say this is rank 1 of nproc 8, blah, blah, blah. Should have 8 lines, not necessarily in order, as we said. Okay, so this is described in the slides. this is what it looked like. It should look like if you do it correctly. So this is making it without any errors. And then this is the, yeah.
Yanni, some people are having issues in the chat. I don't know if you're able to view the chat. It says, Lefteri says that the GOMP module is unknown. He's not sure if he needs to add the path to the module's location. Also, Marco says that the copy gives him a permission denied from the Onyx data IDU12 MPI exec. ED12.
Oh, sorry, MPI. Yeah, he should recursively copy X, not MPI. But you should go down to X because this one you can't copy it because it's the solutions.
Oh,
maybe
okay.
that's the problem. I don't know if that's a problem, but that's one guess. But everything else should be, read, write, read. Okay, Lefteris can't load Compy. This is strange. I don't know, because
maybe
can you see it if yes,
Lefteris is using his own account or the education account? Maybe he's not in the group Edu12 or something else, or another machine.
Hello?
I don't know.
Can you hear me?
Yeah.
Okay. I'm using the educational account.
Okay.
And I do module load go MPI, and it says it's not there. If I do module avail to see what's there, it's not. There's just some core LMod modules. So I said about the path because usually I load modules in other systems from a path, and then that's when they show up. So if you do module avail in your case, we could see what's there. AVA.
This is what I'm doing.
Okay, so I don't have all that. It's just.
You're connected to Cyclone, right? To the...
Yes.
It's weird.
So everyone else is okay with that? It's just me?
Yeah, I don't think it's done here, the loading of the
No, indeed. Even Yanni, even if you purge your modules, I think you can still see all of them, right? Maybe some of them are loaded.
I'll log out and come back or something.
Yeah.
All right, I'll continue, and I will stop to let people try this for themselves, and then we can look at it a bit further. But okay, I think I already said this. Right, so when you're done, you should submit it with sbatch sub 01.sh. And then you can check the job status by using this command, sq -u user. And then you will see the job running something like this. Right, and this job runs very quickly, right? So it just takes a matter of seconds, if not fractions of a second. So you might just see nothing. If you do sq, if you're not fast enough to type sq after sbatch, it might have already been completed. So don't worry if you see nothing. What you should be able to see is that this output file has been created if it's finished correctly. And this is what this output file will look like. So I'll give you, so my clock says 45 here. So I'll give you, well, it's going to go 46 now. So let's, the 50 past, I will come back. You try it for the next 5 minutes. Let's see how you're doing here. Leferi, I think I saw you flash by. Did you fix the problem?
No, I tried again, but still when I do module avail, I don't see the Go MPI. Can we do it in your case again? And because at the top, you can see a path when you do module available. And I suspect maybe that. Yes, that one, that NVMe.
Yeah. But this is not something that you should have to configure.
Yes.
But
let me see if at least it works.
So
Lefteri, what account are you using? Is it EDU
12 EI1?
Okay. It should be the same environment as all the other people, so I don't see why you're having a problem. Let me ask operations.
Okay, it's 50 past. So I will reveal here. Anyway, you would just have to. So this is not very complicated, I know. But it's just so that as a first exercise, we can familiarize with the modifying code, etc. See what problems there are. So that's what your solution should have looked like. Just the MPI-IO world as a communicator. And then for size, we set the number of processes, and for rank, we return the rank, save it, build it, submit it, and it's already done. You should see a file appear, new file, X01 output. If I look into it, then, okay, so I see immediately that I was allocated these two nodes, node 4 and node 5. And okay, rank 1 of 8, rank 2 of 8. So you see that the order here is random. And yeah, that's all. So the order is non-deterministic, said whichever process reaches the print statement first prints, right? So these are just running all asynchronously. Whichever hits the print statement first is gonna print. And there's no guarantee which one that will be. Now, what we could do if we bothered by this this non-deterministic order is we could use synchronization in order to serialize this print statements and ensure an order. And with that, you can use a barrier, and that brings us to the second exercise, okay? So if I go to the second exercise, CD, one folder up and into exercise 02. Okay, so it's basically the same structure as I said, x02.c, a makefile, sub02.sh. Now in Emacs here, I will open x02.c. And okay, I've already filled in MPI-IO size and MPI-IO rank as we did before, copied from exercise 01. Now I have a loop here in which this is looping over the number of processes. And it's checking if the rank is the iteration in the loop and then printing. So, okay, what I'll tell you here is that there is a way I can put an MPI. Well, there's more than one way, but there are ways in which I can put a barrier somewhere in this program. And this will ensure that the order in which the print statements are printed is the same each time. So yeah, so basically that's exercise 2. I would like you to try this. So enter a barrier somewhere in this program, compile it and run it. And if you put the barrier at a correct place, then when you look at the output, then it should be in order. So rank 0 should come first, then rank 1, then rank 2, etc. So please do that. I'm not aware of what the schedule is. So when's the next break is 12:30. Okay. So please do that. And at 12, I come back and we do it again, the solution as we did before.
Yanis, I got an error. I got an error when I typed the make command for exercise 1, which was error 127.
Can you be a bit more specific? What is that?
It says make column, and then it has 3 stars, and then exo1.o in square brackets, and then error 127. Oh, there's also an MPI-IO command not found.
So did you load GeoMPI? Module load?
Oh, okay, I did, but my connection had to reconnect. Okay. Okay, thanks. Sorry.
No, you need to do it when you,
Can I also ask another question? I'm okay with the exercises so far. It's just that since the previous participant mentioned it, I'm using PuTTY from Windows, and very often the connection is dropped and I have to reconnect. And I'm wondering if I'm doing something wrong, or if there's if you might know of any sort of setting somewhere that. Otherwise, I'll just keep it as it is and just reconnect every few minutes. But
I think it's keep alive.
I'm not.
Okay, don't worry about it. I just thought that maybe there was some trivial solution, but don't worry about it. It's fine.
But what did Banayoda say?
I think if you go to, I mean, I've stopped using PuTTY. I've migrated to Visual Studio Code, but that takes time to sort out. But with PuTTY, I think if you go to the configuration and go to connection.
Okay.
I put now in the chat a link. If you look in both Linux and Windows, there is this keep alive option.
All right. So, okay, thanks.
Just look at that link. There is this on PuTTY. You can just follow the connection section. Well, there are some options there. So
okay, I'll read through and fix it. Probably not at this very minute, but when in the next break or something. But thanks.
Okay.
Okay, so let's come back to my Emacs window here. So I need to place a barrier somewhere in this code, as I said, in order to ensure that the print statements happen in order. Sorry, just sorry. Right. So so what exactly is going on here? So so this loop will happen. Well, let's say we're using 8 processes. So this loop will happen 8 times, but only one rank at any given iteration of the loop will fall into the if statement and print, right? So as it is now, the order is again random because we don't know which, because they all execute the loop in parallel, right? So they're all executing the loop, and which one actually reaches this if rank equals I statement first is anybody's guess. But what we can do is force a synchronization at the end of each iteration of the loop. And that will ensure that process 1, for example, will have to wait in here until process 0 goes through the if statement and also comes into the barrier. And then in the next iteration, everybody will be waiting for process 1 to do the print statement and then land inside the barrier before they come out. And then in the next iteration, everybody will wait for process 2, etc. So if you place a barrier here, this should ensure that the print statements come out in order. So let me try this. Sub 2 to this H. Yeah. There it is, done. Let's go 2. And indeed, you should see that the ranks, the print statements are in order of the rank. Okay. Now, this was to demonstrate how the barrier works, to make you think a bit. So the purpose of this exercise was to make you think a bit of how to use the barrier, etc. But in general, you don't want to do things like this in performance critical regions, because this basically serializes this part of the code, right? So if it wasn't a print statement, but was a statement which is, which is actually, you need to do some work in here, then basically you have no advantage of doing this in parallel anymore, right? Because each one will do it in order. So I just want to emphasize that what I did here is just for demonstration purposes. For example, for this print statement, it might be useful if you want to debug your code and see what's happening first and what's happening second, etc., what each process is doing. But in general, this voids any parallelism that you might have expected in your code when you do things like this, okay? Okay, so there's, so here, just to cover the slides, you should see something like this. And the print statement should appear in rank order. So if there are no more questions on this exercise, I'll move on to exercise 3. Just make sure there's nothing in the slide. Okay. Good. Okay. So this is now an exercise that demonstrates MPI broadcast. Again, it's a very simple exercise. If you go into exercise 3, you see that there's one more file than usual. And this is this file data.txt, and all this data.txt is, it has a, it's just a file with a single line, single number. You might recognize that number. This is not so uncommon use case where we're trying to demonstrate here, where the first rank 0, reads a file, reads something from the file, and then wants to send it to all processes. This might be a file with some input parameters, or maybe some small amount of data, right? Like in this case. So that's the use case we're sort of trying to simulate here in a very simple problem. So the root process calls this readline function that I've prepared for you, which basically just reads this and puts it in a double precision number. And then your task is to use MPI broadcast, MPI bcast to broadcast the variable read to all processes. Okay. And if you do this correctly, then you should see that all processes will say the same as we did in the last exercise. So they'll say I am rank, in this case 7, mprog 8 on node 2, or whatever it is for your case. And then it should say got from root variable, got from root variable with value 341415993. If you run it without the broadcast, then only 0 would have this number and everybody else would have zeros. So let me also look at the code a bit. I'm still on the previous exercise. I need to go x03, x03.c. All right, so this is just a function that reads a line from a file and returns it at a double precision number. You don't really need to understand everything here, but if you want to understand it, you can ask me during what time I give you for the exercise. In any case, double precision variable val, rank 0, reads the file, puts it in val, and then there's an empty broadcast here which you need to complete so that everybody has the same value when they print. Okay. So we're at 07 now. I'm looking at my clock here on the top right. It's 12:07. I'll give you 5 minutes until 12 past. Well, it's really 4 minutes, but you seem to be very fast. So. By the way, here's a tip for you. If you have as we do now, we have the module for MPI loaded. You can get the manual entry for any function on the command line. So if I type man, which means manual, man MPI bcast, then this gives me the documentation of MPI broadcast. It gives me basically the call signature with the arguments that can be used. It also has the same for Fortran and for C++, whatever. Actually, no, it doesn't have for C++. But it has a Fortran and explanation and a description here and some examples. So this you can do for any MPI function. It's just a handy tip that you can use if you forget the arguments and things like this. Okay. So let's see how this works. We have a scalar variable to send. So the send buffer should be a pointer to val, right? It's scalar, so it's one element. Its type is double. And then the root process is 0 because rank 0 is the one that has the value. And MPI world is the communicator. That's it. So make should compile s batch xo sub 3 this time. And yeah, that's not me. I guess it's run. What do we see? Yeah, I didn't do the loop with the barrier here, so the output will be in random order. But what's important is that every rank has the same value, which has been copied over from the root process. Just to demonstrate a bit what happens if you don't do this, right? Then what happens? So if I commented out now the broadcast, which means that only rank equals 0 reads this file and puts the value in val. And so what I should see if I compile this program again and now run it, so this is the wrong version that I'm doing now, I should see that everybody else does not have the correct value. Let's see, yeah, everybody is 0 except for rank 0, for which the value is the correct value as read from the file. Okay, all right, I'll fix this back now and make it just to be sure I have the right solution and submit it. And now you see that everybody has the right value. Okay, good. So now I'll move on to the other maybe more interesting collective operations. I'm looking at. Okay, some of you are running ahead to exercise 4 and posting things in the Slack. So I think I will deal with this when we get to exercise 4, if you don't mind. So exercise 4 is a demonstration of the scatter operation. So now I have another file again, data.txt in this folder. Let me move to it. Yeah, so you should all gotten a copy of this file. There are 8 lines. So these 8 lines are some constants. Some of them might look familiar to you. And what I want to do, okay, and well, I should say that I also have now another function called read lines, which basically reads these 8 elements from the file and puts them in an array of vars on the root process. So I think it's sort of obvious what we want to do. You have 8 processes. Rank 0 read a file with 8 elements. So what you want to do is you want to distribute these elements so that each process gets the line that corresponds to it. Sorry about that. Right, the line that corresponds to it from the root process. So there's a scatter operation that is incomplete. Let me open the file. Here we are. Again, this is just this function read lines. You don't need to understand it right now. It just fills in the array with the elements of with elements with the lines of the file. So that's done here if rank equals 0. And so now I want to use the scatter so that each process gets one of these elements, and then they will print and they will say their rank, they will say their process ID, and they will say which variable they have from the root. And if done correctly, then process 0 should have this number, process 1 should have this number, process 2 should have this number, etc. Good. So it is, I guess, by the time I finish my sentence, it will be 18 past. So for this one, I'll give you until 25. Okay. So 25 past, we look at the solution of this exercise, and I guess then we stop for the lunch break and continue. So if you're not quite sure what we said, then of course, I think since you have all the slides available, you can go back to when we talked about the scatter operation. No, this is not that here. Remember what we said, one of the tricky bits is that the send count is the number of elements to be sent to each process, right? So I think that's the thing to be careful about when you're filling this in. Right. Go back to the slide. No. Okay, it seems to have given some of you a bit of a hard time. Let's see what we want to do here. So first of all, I am terrible at remembering call signatures and argument order, so I will have to man it. If you do excuse me, I have to do that and actually look at what's first. So the first is the send buffer, and then it's the receive buffer. Good. So what is the send buffer? In this case, the send buffer is this vars array that root has read. So it's an array, so I can either do that or I can do that, whichever you like. It's the same thing. It's either a pointer to the first element of vars, or it's just vars which aliases to the pointer of the first element of vars. Now, send count. We said this in the slides. It also says it down here. Number of elements sent to each process, right? Not the total number of elements, but the number of elements sent to each process. So we want to send just one element to each process, right? There are 8 processes. And the type is, oh, what's next? Is it the type? Send buffer, send count type. Yes, MPI double. Good. And now it's the receive variable. So that will be var 1 MPI double. What else do I need to specify? Root 0 and MPI com world. Good. Let's see what we did here. Make dispatch sub 4. Still 0. Okay. Sub 4. Output.txt. Okay, it's not in order because again I didn't do this barrier thing here. Let's just, so here's a tip. You can pipe this through this sort function if you want to just sort the output of the file in the command line. So this will just help me comparing with the file data.txt and confirming that indeed, oops, start. Yeah, so indeed rank 0 got, so the sort function I just piped the output to sorts it, well basically it'll sort it on this character here because all the characters before it are exactly the same, right? So that's just a nifty way of just getting the output in a sorted way so I can compare with this file. And indeed, each rank got the elements that corresponds to it, okay? Some of you had a bit of a trouble here. Yes, okay, I already see some of you figured out it was a problem with addressing the points. Good. Okay. Yes. So if there are any questions, I'll be happy to take them now. And I think it's not enough time. Well, it's already past. And so I think there's a 1 hour break now.
Yes, 1 hour, but we'll be online. So I'm not going to close the connection. So people can ask a question, then whenever somebody can look at it, they'll do so and answer, I guess. But we begin again at 1:30, so we can go on break now, and please be on time at 1:30 to begin the next session.
We're going to continue with the exercises after the break? Or?
Yes, we'll continue with the exercises of the, so we'll do the gather and the reduction. And then we will do point to point and some exercises on the point-to-point. But immediately afterwards, we continue with exercises, yes. Okay, so see you. I'm going to stop sharing now.
Okay, so we begin again at 1:30. Thank you very much, everyone.